Did you know that at one point, the US government was losing nearly 4 cents just to produce a single 1-cent coin? Yet to create something that was already unprofitable from the moment it was born, they still had to consume tons of valuable metal and push it through a series of brutal industrial processes, from blanking and red-hot annealing to chemical treatment and high-speed stamping, turning these tiny objects worth only 1 cent into one of the strangest economic paradoxes in the world. But behind those massive production lines lies far more than just money manufacturing. It is a story of metallurgy, precision engineering, and anti-counterfeiting technology that has evolved for centuries. Today, join Factron Process as we step inside the mint to uncover how a coin is truly made. Coins are one of the few objects that people handle more than almost anything else throughout their lives. A single quarter can pass through the hands of tens of thousands of people over several decades before it is finally removed from circulation. Each year, more than 14 billion coins are produced from alloy coils, measuring roughly 1,500 feet in length, about the length of 4 to 5 football fields laid end to end. Inside the mint, high-speed industrial presses operate at astonishing rates, capable of striking up to 750 coins per minute. So fast that the human eye can barely distinguish individual coins as they are formed. And that is only a small glimpse into the journey behind these tiny pieces of metal, worth just a few cents, yet which have remained an essential part of the modern economy for centuries. Everything begins with the design. Before a coin can enter circulation and end up in millions of wallets, cash registers, and vending machines, it must first be developed by artists, sculptors, and engineers using advanced digital design systems. Today, most coins are created with CAD software, computer-aided design technology that allows artists to control even the smallest details on the coin's surface with remarkable precision. Features that appear simple at first glance, such as strands of hair, facial contours, or lettering, are actually calculated and refined with great care to ensure they are both visually appealing and difficult to counterfeit. One of the most famous examples is the American Lincoln cent. The portrait of Abraham Lincoln on the 1-cent coin has remained in continuous use since 1909 and is still the longest-running design currently featured on any US coin. But coin design serves a purpose far beyond preserving history. Microscopic engravings, reeded edges, and raised relief structures also function as physical security features, helping protect the currency system by making counterfeit coins far more difficult to produce. Once the design has been approved, it is not stamped directly onto the coin. Instead, it must first be transferred onto a steel striking die. This is one of the most critical stages in the entire process, because the quality of every coin ultimately depends on the precision of these dies. Engineers use CNC engraving machines and laser technology to create a master hub, a hardened steel block that contains a raised, mirrored version of the coin's design. From this master hub, multiple working dies are produced to support large-scale manufacturing. Each working die can strike hundreds of thousands of coins before it begins to wear down. For this reason, mints must maintain an entire system dedicated to the continuous production, inspection, and replacement of dies behind the scenes. Interestingly, every detail on a die must be engraved in reverse. Even the smallest error can be disastrous. If a single feature is engraved incorrectly, every coin struck from that die will be defective and must ultimately be melted down and recycled. With the dies ready, the production line can finally begin receiving its raw materials. Massive metal coils are delivered to the mint by specialized trucks or cargo transport systems. Each coil can measure up to 1,500 feet in length and weigh more than 4 tons, roughly the weight of a small truck. The composition of each coil depends on the type of coin being produced. Modern quarters and dimes are primarily made from copper-nickel alloys, while the penny has a very different structure. A zinc core coated with a thin outer layer of copper. This approach dramatically reduces production costs, as the price of pure copper has become far too high for everyday circulating coinage. The coils are then loaded onto automated uncoiling systems. Giant reels slowly unwind the metal strips and feed them continuously into the blanking line. Even at this early stage, the scale of the operation becomes clear. Coin production is far more than simply printing money. It is a large-scale metallurgical industry built around moving, processing, and transforming enormous quantities of metal with remarkable efficiency. The long metal strips are then fed into a blanking press, a high-speed punching system that operates much like a giant industrial cookie cutter. As the machine runs, a series of punches repeatedly press into the metal strip, cutting out perfectly round discs known as blanks, or planchets. The speed of this process is remarkable. Some blanking presses are capable of producing tens of thousands of coin blanks every minute. Each disc must be manufactured to extremely tight specifications, because even the slightest variation in diameter or thickness can prevent a coin from functioning properly in vending machines, parking meters, or bank counting systems. Meanwhile, the leftover metal surrounding the punched blanks forms large sheets of scrap known as webbing, which resemble giant metallic honeycombs. Rather than being discarded, this material is shredded and returned to the metallurgical process for complete recycling. This is one reason why modern mints operate with such high material efficiency, wasting virtually none of the metal that enters the production line. The freshly punched coin blanks are still too hard for the final shaping process. To prepare them, they pass through annealing furnaces operating at temperatures above 1600 degrees Fahrenheit. Millions of blanks move continuously through the furnace until the metal glows red hot. This heat treatment changes the internal structure of the metal, making it softer and more ductile, while reducing the risk of cracking during striking. The furnace atmosphere contains very little oxygen and is carefully controlled throughout the process. From the outside, streams of glowing metal discs moving along conveyor belts make this stage look more like a steel mill than a coin factory. As soon as they leave the annealing furnace, the coin blanks must be cooled almost immediately. If the remaining heat is not properly controlled, the blanks can stick together or damage the freshly treated metal surfaces. To prevent this, they are sent directly into a specialized cleaning and chemical treatment system. Water serves as the foundation of the process, but the treatment solution also contains lubricants, antioxidation agents, and various cleaning compounds designed to remove contaminants left behind after heat treatment. In the case of pennies, the solution often includes citric acid, which removes copper oxide from the surface without affecting the thin copper layer beneath it. The blanks then pass through several washing stages to remove metal dust, industrial oils, and any remaining chemical residues. Some facilities use massive rotating drums that tumble and clean millions of blanks at a time, while others rely on automated bucket elevator systems to move them through a series of treatment tanks. By the end of this stage, the coin blanks emerge bright, spotless, and fully prepared for the final shaping process that will transform them into recognizable coins. Before they can become finished coins, the planchets must pass through an upsetting mill, a machine that forms the raised rim around the edge of each blank. Although it may appear to be a simple step, it plays a critical role in the minting process. The machine works by forcing each planchet through a narrow gap that is slightly smaller than its current diameter. Pressure applied from both sides causes the metal around the edge to flow upward, creating the distinctive raised rim. This rim helps protect the coin's design from wear during circulation. More importantly, it allows the planchet to fit precisely inside the collar of the coining press. Without this raised edge, the immense striking forces used later in production, often reaching hundreds of tons, would cause the metal to spread outward like a flattened metal pancake. The rim also serves a historical purpose. It helped put an end to coin clipping, a common form of fraud in the past when coins were made from gold or silver, and people would shave small amounts of precious metal from their edges without immediately being detected. This is the most important moment in the entire production line, the point at which anonymous planchets officially become real coins. Each blank is precisely fed between two dies inside a coining press. As the machine cycles, the upper die comes down with a force that can reach hundreds of tons, while a surrounding collar holds the blank firmly in place to prevent the metal from flowing outward. In just a fraction of a second, every portrait, inscription, number, and microscopic detail on both sides of the coin is pressed deep into the metal surface. The speed of this process is remarkable. Some modern coining presses can produce up to 750 coins per minute. That translates to more than 45,000 coins in a single hour of continuous operation. But speed is only part of the story. Every strike must maintain an extremely precise level of force, alignment, and consistency to ensure that every coin leaving the press is virtually identical to the next. For proof coins made specifically for collectors, the striking process is repeated multiple times to create mirror-like surfaces and exceptionally sharp details. It is here that a simple metal disc completes its final transformation, becoming a piece of currency that will eventually pass through countless hands in everyday life. Not every coin successfully makes it through the production line. After striking, the coins pass through automated quality control systems equipped with high-speed cameras and precision measurement sensors. These systems are designed to detect defects such as off-center strikes, missing details, scratches, surface blemishes, or deformed edges. However, automation alone is not enough. Quality inspectors continuously remove samples from the line for manual examination, using both visual inspection and magnification equipment. A single flaw in a die can quickly become a major problem. If a defect goes unnoticed, thousands of coins can be struck incorrectly within just a few minutes. Coins that fail inspection are sent to a machine known as a waffler, which bends and distorts them into a waffle-like pattern to ensure they can never re-enter circulation. The defective coins are then melted down and recycled back into the production process. This rigorous quality control system is one of the reasons modern coins achieve an extraordinary level of consistency, even though billions of them are produced every year. The coins that pass final inspection are sent to the packaging area. Here, automated systems begin counting, weighing, and sorting each batch with an extremely high level of accuracy. Even a small discrepancy in quantity or weight can cause an entire shipment to be held back for further inspection. Once approved, thousands of coins are poured into massive industrial bags. When filled, each bag can weigh thousands of pounds, making manual handling impossible and requiring specialized forklifts for transport. The bags are then stacked onto pallets and moved into secure storage facilities. However, not all coins are packaged this way. Many are sent through automated coin rolling lines, where machines count the exact number of coins required, stack them into columns, and wrap them in paper or plastic at high speed. These rolls are then boxed, sealed, and prepared for shipment. For proof coins and commemorative issues intended for collectors, the process becomes even more careful, with each coin protected inside specialized holders or presentation packaging to preserve its flawless surface. From there, the coins begin the final stage of their journey. They leave the mint, pass through storage facilities, banks, retailers, and payment systems before eventually finding their way into the pockets of millions of people. What makes this especially remarkable is that despite the growing popularity of electronic payments, billions of coins are still produced every year to serve vending machines, parking meters, laundromats, and countless small transactions that continue to take place every day. A coin may seem simple, but behind it lies an enormous manufacturing system that combines metallurgy, precision engineering, industrial chemistry, and large-scale quality control. From massive metal coils weighing several tons, to red-hot furnaces operating around the clock, to high-speed presses capable of producing hundreds of coins every minute. Every stage must function with extraordinary precision to create something most of us use every day without giving it a second thought. What makes this even more remarkable is that this entire complex process exists to produce an object worth only a few cents. Yet these small pieces of metal continue to play an important role in billions of transactions around the world each year. They appear in vending machines, parking meters, laundromats, checkout counters, and countless other parts of everyday life. And perhaps the most fascinating part of the story is that even as the world moves steadily toward digital payments, mints continue to produce billions of coins every year. That raises an interesting question. Will coins eventually disappear like so many older technologies before them? Or will they remain a necessary part of the economy for decades to come? The coins in our pockets today still carry with them more than 2,700 years of history, and the output of an industrial process that has never truly stopped.